All right, so the first panel is titled How Rapid Technologies Are Changing Our World and Work. And let me first introduce the panelists to you. All the way on the end, Vince Rossi and Adam Mettello from the Smithsonian Institute, Smithsonian Art Museum. How do I say that?
Smithsonian Institution.
Okay. Dr. Stephen Rouse from Walter Reed Army Medical Hospital. Jeff Hosfeld from Whiting-Turner. And Peter Schlein, Mark Schlein, Product Development Facility, U.S. Army. Great. And I'm Jan Baum. I'm the founder and director of the Object Lab at Towson University. And I'm going to moderate this morning. So I'm going to start so that I can then kind of maybe recoup some time and get back on track. So the format is we're each going to talk for about 8 to 10 minutes, and then we're going to open up to you for question and answers. So again, we really want this to be conversational. You're the reason for the event today, and you're what's going to carry us forward. So we're going to turn it over to you. Rapid technologies are changing the way we make things across industries. These technologies are digitizing the physical world. The Object Lab is a research-based, educational, state-of-the-art rapid technologies and digital fabrication lab, one of a few in the country. Our lab is comprehensive. It includes 3D scanning and imaging, high-level 3D computer-aided design, laser cutting, CNC milling, and we have 4 different types of additive manufacturing or 3D printing. Our competitive advantage is that we're a comprehensive state-of-the-art lab. We move from 3D scanning and data collection and modeling to cutting and printing, all in one place. Students learn firsthand how the technologies interface with each other, the application of one technology over another, and the pros and cons of each system or technology. We're preparing students with a broad set of rapid prototyping or rapid technology skills who can work in any number of companies in the Baltimore region who employ rapid technologies. We're digitizing and digitally creating the physical world, and in today's world, a stationary product is a target. Rapid technologies help us to compete. The industrial 3D printing systems start at $15,000. So Dave showed you the range there from maybe $1,200 to $1.4 million. Industrial applications start at $15,000. 3D printing technology is a disruptive technology. It's a game changer. It's changing how the physical world is made, where the physical world is made. It's changing what the physical world looks like, and it's changing who makes the physical world. It's changing our world. Aerospace, healthcare, auto industries are already there. Early adopter consumers are increasing, with consumer 3D printing systems starting at $1,200. And one of those systems stole the Consumer Electronics Showcase show this year, and they're out on our floor today, MakerBot. Coverage of this technology has exploded in the media over the last few years. In February of last year, The Economist predicted that 3D printing was likely to disrupt every field it touches, and it said in the long run, 3D printing will expand the realm of industry and imagination. This week, only a little over a year later, in a special report on manufacturing innovation, The Economist referred to the digitization of manufacturing as the third industrial revolution. The pace at which these technologies are moving is fast. It's critical for institutions of higher ed to have innovative facilities such as the Object Lab and distinctive programs that educate about these technologies as a whole and engage a range of new ways of working if our goal is to educate the future workforce and leaders. Many people are sounding the alarm bell about America not making what it invents and innovates, from Xerox to DARPA, and many people and entities in between. And I think it was Adam Smith who said early on, or an early warning, that it's not prudent to rely on our neighbors for critical supplies. And I think that this is a bell that we keep hearing over and over again, and I want to make sure it's ringing for you if it hasn't already. Today, there are new forms of manufacturing, and manufacturing is changing with these technologies. President Obama's Advanced Manufacturing Partnership is an initiative with business and universities to create jobs and boost competitiveness. As The Economist cites, increasingly manufacturing is not on the factory floor, but in office parks carried out by designers, IT specialists, logistical experts, and many more specialists. The lab is an excellent educational resource not only for the university, but the entire region. For people to be able to learn about these technologies in one place is fantastic and unparalleled. We routinely host open houses, special events, and small groups. I know some of you are saying, how can I get into one of those? I've been asking for a while. We'll get back to you. The lab is busy all day, every day. And so a lot of the students that stood were my students. My colleague Joshua DeMonte is here. And the students will attest that one of us is in there all hours of the day and on the weekends as well. Our students, staff, faculty, and partners say they love working in the Object Lab because it feels like an important place to be, and we agree. Local businesses and entrepreneurs can access these technologies, learning how advanced manufacturing can help their businesses succeed and stay competitive in today's global world. Inherently interdisciplinary, we seek collaborative relationships with a broad array of industries, from the creative industries to science and manufacturing. We want to work with you. Collaboration is key, and we need to collaborate in order to compete. When I designed the lab, I did so with the notion of diversifying the rapid tech resources in the region, capturing various printing technologies and approaches while not overlapping other institutions. We prefer to partner with our peers. Some of the stools in the lab were designed by the Object Lab team, and it is a team. It's been a team from day one that put that Object Lab in place. I happen to be the leader, but it's a team that's gotten us our look, things like the customized stools in the lab, etc. Right now we have so the stools were designed by a team. They're manufactured at CCBC's Fab Lab. We want to partner with our peers. We want to collaborate to be competitive. Right now we have a collaborative project with a new product development class at Johns Hopkins University with Mike Agronin, and I know Mike Agronin from working with Mike Raphael. I'm surrounded by Mikes these days. When I talk to my family, they're like, which one is that? Which one now? Our interns from the Object Lab provide design skills and expertise as well as rapid prototyping experience to an array of Johns Hopkins students, and I think that is really exciting. I know Mike does too, and we're going to continue that. And to our colleagues that feel a little envious of our lab, I would say, let's collaborate. How can we come together to strengthen the people that we're educating, to strengthen the region in rapid technologies? Let's collaborate to compete. Giving students access to cross-disciplinary learning experiences, modeling collaborative working relationships, and introducing them to an array of regional industries engaged in rapid technologies are all significant in educating people for the 21st century. Students today understand the world is global. They understand these technologies can open up many more possibilities. And when they have a sense of their regional network, they can more easily find their place in it. And it is higher ed and it is educators' responsibility to help students find their way through this. The lab being innovative and the programs associated with it are an essential 21st century resource. One of the things I'm most excited about is being a new model for doing business. Originating in the university, we train future workforce and future leaders in rapid technologies and advanced manufacturing. We work with industry partners, the entrepreneurial community, advocacy organizations, and government to advance the rapid tech agenda in Baltimore for positive economic impact. To create this crossroads at the lab is essential for 21st century success. The future is not going to be determined by a single sector or a discipline. The challenges we face now and will face in the future will require collaborative, forward-looking, and entrepreneurial relationships between education, industry, business, and government. We're in a global marketplace, and we can strengthen our region by working together. We must cross-pollinate for the win. The emergence of rapid technologies is signaling a new industrial revolution. Next generation making is flexible manufacturing, printing parts on demand, producing parts in small batches, customized manufacturing, and local manufacturing. From pharmaceuticals and medical implants to art and invention, the whole gamut. Rapid technologies help us compete. When we're engaging the local business community, we're looking for the triple win, meaning we want to work with manufacturers who can also bring in third-party aftermarket businesses as well. Next generation manufacturing is open, engaging new ways of working such as online platforms, accessible tools, digital libraries. I think they're a little bit closer than maybe Dave does, but I think I work on a different scale than Dave does. And distributed networks lead to innovation in products and business models, and we desperately need that. And perhaps most important, these new ways of working empower individuals to imagine, create, invent, and innovate, spurring entrepreneurship. New open ways of working capitalize on our collective intelligence and our desire to contribute to society and to be of use. The accessibility of new technology spurs innovation by giving individuals access to testing ideas and experimentation, resulting in more players in the game. The Object Lab offers services to local businesses guaranteeing security. Integrating real-world experiences into the classroom enhances our educational offerings. Educating students about new markets, the entrepreneurial process, and business in general. We cannot miss this piece. Bring your ideas to us about how you might use rapid technologies to advance your business. bring those to the Object Lab. Designers are natural problem solvers. Let us partner with you, give us your R&D problems, and let us be your rapid prototypers. The lab is located in the Art and Design Department in the College of Fine Arts and Communication under the leadership of Dean Susan Pisinic, who is with us today. Imagination, creativity, design thinking, new ways of working, rapid technologies, and an entrepreneurial spirit are a few of the 21st century skills our students need in order to shape the future of making and manufacturing. We look forward to forging partnerships with regional companies such as Under Armour and Black & Decker and Danco Arlington and many others that are out there. If I didn't list you, and you know I don't know about you, please come and find me, because I want to be on your radar and I want you to be on my radar. Our faculty are in many prominent arenas, from leadership roles in events like this one today, to prominent trade shows like the International Gift Fair, to having solo shows at cultural institutions like the Delaware Center for Contemporary Art in Wilmington, to being recognized by iconic cultural institutions like the Smithsonian Institution in exhibitions that are upcoming 40 Under 40. Our students are routinely employed. A few weeks ago, one of this year's undergraduate seniors, this is going to horrify her, Megan Dattori, will you please stand up, Megan? You can either, exactly. I gave her 4 years of warning to participate, and to those of you who have not graduated, participate or you'll get called out at the next event. A few weeks ago, Megan Dattori was awarded an internship in the 3D model shop at the Smithsonian Art Museum. This is her dream. It gives me immense pleasure to help her realize those dreams. When they called her, they told her she was the strongest candidate because of her rapid technology skill set. The Art Museum. It's not just about manufacturing. I think manufacturing is very important, but it's not just about that. This is across the board. Later this evening, along with 4 of her peers, some of which are here today, and some are not, but that's okay, she will present a year-long honors project. She undertook a year-long project with the Honors College to produce a body of rapid prototyped rings that examine the issue of ADHD. And their opening is tonight from 7 to 9 at Lodafon in the Station North Arts District, and that's where I will be after this. Graduating an undergraduate art and design student who put together a collection of work that is rapid prototyped and addressing an issue like ADHD, I think we're doing something right at Towson University. A Center for Excellence, the Object Lab at Towson University, is leading outside and working outside, and thank you, Dr. Galeazzo, for those words, advancing rapid technologies for the greater Baltimore region. And I'm just going to close with one of my favorite quotes. Ursula Burns, the chairman and CEO of Xerox Corporation, said this to the National Academy for Engineering recently. She's also a member of the President's Job Council. It's time for us to be impatient with the way things are. It's time to celebrate impatience and get on with it. And by it, she meant getting serious about education, innovation, and manufacturing, breaking the gridlock and creating policies and infrastructure that support a strong U.S. economy. History proves that when industries are disrupted, incumbents lose. Towson University is not an incumbent. We are fulfilling our role as a resource for the state and the nation by developing skilled knowledge workers for the 21st century who can solve problems and contribute to the well-being of society. That's all for me. Any one of you can jump in next. Or Amy, who do you have queued? Okay.
Good morning. It's always humbling to talk to a group of people who have either experiences or talents that far exceed your own, but we all play a role. And I've been in it a long time, as the Greg will tell you, and as Mr. Burns said, import to the digital world, but are those just going to, those can just roll through. I run the U.S. Army's Saberni Product Development Facility. And let me just say right now, many industries like their acronyms, nobody better than the government. And Saberni stands for Chemical, Biological, Radiological, Nuclear, and Explosive. It's defense against those things, weapons of mass destruction. We essentially are a rapid product development facility that very quickly produces a solution when a problem comes up, either here in our country or for our war fighters. And over the years, a bunch of years now, we've been very progressive at implementing these new technologies. And just to give you an idea, we started with CAD in 1977 or 78. We started with, I personally in 1982, we started with additive manufacturing in 88 or 89 with stereolithography, with FDM in the mid-90s, along with LOM, for those that remember that technology. And right now we have probably a dozen different technologies that we implement on site. But I think one of the big lessons that we've learned over the years, you always want to be out there in front, and heck with a level playing field. That might be political, but forget that. You always want to have the advantage. And by using and looking at these emerging technologies, you can take advantage of those things. But you can't forget the real productive technologies either. And I think one of the messages that was there in Mr. Burns' talk that I don't think he got played up enough was he wasn't just using additive manufacturing technology. He was taking a technology that's tried and true, casting, and he was using additive manufacturing to enhance a traditional manufacturing process. And we've done that dramatically. We have all the additive manufacturing technologies and all the 3D data capture technologies, but we also have the traditional technologies as well. And doing things well is to know when to use which of those technologies. And then, of course, employ the people who do it really, really well. And that's a lesson for the students. Whatever you do, have fun doing it and do it really, really well. Because if you don't, find something else to do, because you won't make your mark. We have done quite a lot of diversity in the kind of work we do. Our folks have a lot of fun. The picture you see on the screen there was it's a UAV that can collect aerosols for either radiation or biological or chemical contamination, and then alert folks that can track and follow. And last year at the Fukushima disaster after the Japanese tsunami, we prepared one of those units to send over there so that it could track the plumes for the radiation. In fact, it actually didn't fly. There was political issues with frequencies and treaties. But another one of our units that we developed, which was a little ground robot that we had set up with all kinds of sensors. We sent one of those over there. And the fun part about this, and this shows how all the industries work together, we did develop this, but we did it in partnership with a company that makes those little robots. The company's name is iRobot. They make the PackBot. They also make those little vacuum cleaner robots that you see rolling around. But they gave us, one, because we're the government and not in competition with them, and two, because we showed them an extreme level of competency. They actually gave us access into their source code for their robots, something they never gave to anybody else. This allowed us to go in and take our chemical sensors and our rad sensors and whatnot and interface them in such a way that if they sense something, automatically right on the control screen, boxes would come up with things and go. Now, the neat thing about that was we put the cost into developing this for our own need to experiment with this, but we didn't go all the way. We didn't try to actually update that robot to have all the latest things, but we turned that over, and what they got out of it is everything we developed, all the code that we wrote, became theirs. They turned that into a commercial product. Now, in Japan, when they had the Fukushima disaster, iRobot donated 2 robots, and those robots had all the technology that we had developed integrated into them as a commercial product. So we had made that interface together with our partners. Again, one of the limitations of current additive manufacturing technology is we focused on geometry, and we're limited to these layered manufacturing. And if geometry is the driving factor, then we've got it. And we start, some of these biological things that we're talking about are great, but very frequently we're looking for higher performance. We're looking for things that not only are the right shape, but have the right strength properties, or have electrical, electromechanical, electrochemical aspects at the same time. And so I think the future for these technologies, again, is to be looking at how can we take these multi-material processes, how can we take some of the conventional processes that are really, really good at material things and combine them instead of continuing to do with the conventional processes, but combine together the additive manufacturing processes and and those other things. I think that's the future of where we're going with these things. I'm going to leave it there. I can answer anybody's questions. Be happy to do that, but we're a little behind, so go from there.
Great, thanks. Dr. Rouse.
I'm the next one up. I'm really glad to have the opportunity to be here. As a matter of fact, when Michael Raphael asked me if I would be willing, I totally forgot that the whole rest of this week I was in California at the Additive Manufacturers Users Group meeting. So I left there last night, got here about 2 o'clock this morning. I'm still awake, thanks to additive manufacturing. Now this slide is an important, is a very important thing for you to keep in mind. This comes down to the, even more basic than the way Dave said it. This is the accepted definition of additive manufacturing now. We are still running as an industry into the problem that the media drives our terminology. So folks, 3D printing, rapid prototyping, gone. This is additive manufacturing. In medicine, and you can go ahead and just, I think there's maybe 6 or 7 here. In medicine, the difference between manufacturing and prototyping really doesn't exist unless you're doing medical devices. When you're working on patient models, what you're doing, you may be making one-offs in plastic that are going to be thrown away in a week or 2, but it's still a final product, so it is a manufactured product. One of the things that's a concern to me in our discussion here, and I'll bring it out a little stronger in a minute, is that we are not going to be getting rid of traditional technologies. There's always going to be an appropriate place for the traditional technologies, but somewhere along the line you have to make decisions. Can I use an off-the-shelf or an over-the-counter product, or do I need to create a product that's specific for a single patient or for a single purpose? And when you start getting into the one-offs and low volume production, you're no longer in a cost-effective way of being able to do that using standard manufacturing technologies. And you can flip through these too. As you read your newspaper and you look at stuff online, what you're seeing now is you're seeing article after article after article about things that are tailor-made for the individual. And he mentioned, Dave mentioned that this is already very strong in medicine. I got news for you, it isn't. And I wish I'd had a chance to mention that to him. Almost all orthopedic implants are made using traditional manufacturing. They may be using rapid manufactured, additive manufactured, rapid prototyping, whatever you call that, for cutting guides for those knee implants, but the bulk of those things in the United States are done using traditional manufacturing techniques, and in most cases are quite effective. But all you have to do is look at the fact that we have 900,000 joint replacements this year. And in most cases, you might as well plan on a repeat surgery 12 to 15 years from now for each one of those cases. Because of the difference of what we can do using additive technologies in building and designing different things that are specific for that patient, we can create products that will last far longer, integrate better with the human body, and create a lower cost to us as taxpayers within our healthcare system, and this is very important. Go ahead and, there we go. Now, you're wondering how, by profession I'm a dentist, I'm not an engineer. But I got involved in aluminum and steel casting when I was still a preteen. Went into bronze and precious metals, then printing, and then into dentistry, and almost all my care has been hospital. But because those of us who have to work with the government have some restrictions, and we didn't get word about having slides for this, I didn't get the opportunity to get approval on a presentation. So I kind of cut and pasted bits and pieces of things that I had approval on, and I like this because this is an off-the-shelf product. You pick for the patient what you want, then you very carefully go into the lab and you set all those teeth in wax, and then the next slide shows the end result. Just because I can do something using this technology doesn't mean it's the thing to do, right? I mean, it looks good. Go ahead. Using traditional technology, we've got your standard plates and screws out of titanium for patient cases, and in most cases, I would say, other than the frontal plate on the side there, those should work pretty good. That one would probably work, but it's a combination of hydroforming and some other things. It's a little bit difficult to work with, and it's very expensive. If you think about the cost as a healthcare provider, you think about the cost, and I buy a 4-inch square of titanium sheet like this with the holes in it from Stryker, and it cost me $4,000. Guess what it turns around and goes to the patient for? I can make that out of titanium using the electron beam process. I make my own plates with fixation involved, already designed in it, and I've got about $60 worth of titanium, maybe. So when you're looking at the material that you're using for the process that you want to do, you've got your traditional casting, milling, molding, forging, your hydroforming and those, and then you've also got the additive manufacturing. Additive manufacturing gives you the ability to combine shapes and contours and complexity, internal and outside, that you simply cannot do any other way. So when we look at these, you know, I'm used to using a clicker in my own hand, so I can zap down through these. One of the easiest things to look at is, what is it I want to build? If I can do it using standard technology, it's probably cheaper. Not much point in doing it. If I need internal geometry, I cannot mill that, I can't stamp it, and most of the time I can't cast it or anything else. So we want to reduce the cost. We want to be able to use variable material properties in a long bone implant. Very often it's handy with these materials to be able to vary the stiffness of the outer shell and have an internal geometry that allows that to flex so that it doesn't get stress shielding for the bone and create additional problems later on. So one of the things that we have really found using this technology, whether it's just in pre- and post-operative models or in custom implants, is that we are dramatically reducing the surgical time involved in these procedures. That has several things involved in it. One is that by shortening the surgical time, we reduce the amount of bleeding that you are going to do. We are going to reduce the amount of anesthesia that you have to have. We're going to reduce the amount of exposure that the wound has to the air. So all of the additional factors, what they call the morbidity factors to the patient, are going to be reduced. We are bringing, in many cases, surgeries that have taken us 6+ hours, we're taking them down to the 60 to 90 minute range. $66 a minute for an OR 5 years ago. I doubt if it's any cheaper now. So if we can save an hour, we can save a half hour. We've made a significant savings to the institution. Maybe not to the patient, but if we do this correctly, we as an industry have the ability to bring the costs of the provision of health care down, and that's going to help us a lot, particularly in terms of what they're talking about now with the costs of health care skyrocketing. The other thing is that the end result of the surgeries is superior, and in many cases we're able to do in a single operation what previously would have taken several. Go ahead. Different processes and materials that you're all used to using. I think the plastics, the PEEK and PEC and titanium, cobalt chrome, and those. Go ahead and slip on to the next one. One of the things that speeds us up is doing things like either custom fixation or simply building a model so that the surgeon can take this model into his office and pre-bend the plates before going into the operating room. That simple little procedure saves 30 to 45 minutes of surgery just by being able to sit down at his desk with a cup of coffee and pre-bend the plates that fit on there. The next one shows the plates. And then this was a design for a custom fixation plate that we did for a complex pelvic fracture, and the next one shows the actual plate the way that it was produced. This was the way the surgeon designed it, and it worked out perfectly. Next one. The next couple of slides just show some examples of products that were built using the electron beam or E-beam system from RCAM. Next one is a pelvis, I believe. Okay. When we talk about needing to go back in and do repeat surgeries, this is a good example. The photograph on the left shows the hip stem, which you can identify fairly easily. You don't see the leg. But up above it, you can see what looks like a cap with a hole in it. That should be the acetabular cup that joint fits up into, and instead, the whole bone around that acetabular cup is gone and it's pushed up inside. If instead of modifying the patient to fit our off-the-shelf product, we build a product to fit the patient, we're all better off.
It's really hard to do this, and I know no one wants me to, but I need to pause you and move on to the next panelist.
I figured.
I do apologize. Next up, Vince Rossi and Adam Metallo from the Smithsonian Institution.
Thanks, Jen. My name is Vincent Rossi. This is Adam Metallo. We both work for the Smithsonian Institution. So we're building a 3D digitization unit. So right now it's just the two of us, but we're basically laying down the foundation for a larger department. So we can start off by giving a little bit of background on the Smithsonian. So a lot of people think of it as one museum, and it's not. It's actually 19 different museums. And there are also 9 research facilities located around the world. And it's those research facilities that really drives the mission of the Smithsonian. So a lot of times we'll start working on a project and get connected at the research level, and then see the life cycle of that project through all the way out to public access. So that could be supporting doing some 3D scanning in the field in Chile or somewhere around the world. 3D printing replicas for research purposes, and then also creating 3D models that can then go on a website or actually be part of a physical exhibit. So the Smithsonian's collection in its entirety is estimated at 137 million specimens, works of art, and objects. And I think it's less than 2% of that number that anyone can actually see. So if you could make your way to Washington, D.C., you can only see a very small portion of that collection. And that's where we get really excited about 3D technology. So how can we 3D scan objects and deliver that content to the world? So there's a whole lot we get to see because we work as employees. So we go to these facilities where we can see aircraft that no one else gets to see. So we think it would be fantastic if we could use 3D technologies to then deliver that to the world so everyone else can have that same opportunity. And we'll have some slides cycling through, and at some point we might address each one individually.
So our background is actually in the exhibits model shop, and that's how we got into this game, I'd say. So we came from a traditional model making world where it was sort of lovingly handcrafted. We eventually got a laser scanner in order to make more accurate replicas for display, and from there we realized that there were much more profound implications. So at this point, what our role is to figure out how to scale up digitization of collections and sort of provide access to 3D models on a Smithsonian scale and public access in general.
So of course, we're not there yet because you're looking at the department, right? So there's only so much we can do. So our strategy is to pursue use cases that demonstrate how the technology can be used. So right now we're cycling through the video, but can we go back a few slides? Maybe we could talk about a few of these use case projects. So here's the gunboat Philadelphia. We were working with Michael Raphael of Direct Dimensions. This was 3D scanned using a medium range laser scanner. So here we're looking at a surface model. So the powerful thing about this project is that how many people know about this object, first of all, the gunboat Philadelphia? Has anyone seen it or they know about it? So a few people, that's good to see.
It's more hands than we get at the Smithsonian, actually.
That's true. We presented this to the secretary of the Smithsonian, the man in charge. And he was like, that's in our collection? And we're like, yeah, it is. So it's the way it's displayed is not ideal. So it's an iconic object. It was used in the Revolutionary War. It supported a 40-man crew, so 40 men lived on this crew. It's largely seen as the beginning of America's first Navy. So it was sunk in, I think it was 1776 in Lake Champlain. The museum, the American History Museum, was literally built around this object. But if you go to the museum, you could see that it's not displayed ideally. It's actually walled in on 3 sides. So you could see it from like one perspective. So now, using 3D technologies, we can get a 3D model, and anyone can now, or actually the researchers can now see the boat from different angles that they haven't seen, that haven't been possible since the late 1950s. So this is a really powerful use case. It also helps to raise the profile of this object, so we think it should be much more recognized. We could maybe go to the next slide.
This is an object from the Freer-Sackler Gallery. So this is called the Cosmological Buddha. So it tells the story of enlightenment from top to bottom in low relief carving. At the top you have enlightenment. At the bottom you have stories of terrible things happening in hell. In the middle somewhere is Earth. So what we're going to do, or what we have done, is laser scan this object, and we hope to actually pelt this object and digitally unwrap it so that we can actually look at high resolution, flattened out models. That's going to be a much better delivery mechanism for research and public access, actually, because in the gallery it's absolutely stunning. It's a incredible object, but it's very hard to read and discern the stories that are happening and going on. So we're going to be able to reinterpret this in a way that could be much more meaningful for general audiences and researchers alike.
Go to the next one. So here, we were recently, one of our recent field projects, we were in Chile working with the Natural History Museum. So we collaborated with National Geographic, the Chilean National Museum, and our office, the Digitization Program Office. So it's a pretty cool backstory. They were widening the Pan American Highway in Chile, and in doing that, they uncovered over 40 complete fossil whale specimens. So they stopped construction, they started excavating those fossil whales, but that contextual information was lost, and that's very important for research. So we were able to get down there pretty quickly. Within a month and a half, there were only 8 fossil whales left, so we 3D scanned all of them. The traditional method of documentation, and this is pretty much for all field work, it's pencil and paper, and it's drawing out like meter by meter string lines, and you're sort of sketching the approximate location of each fossil. Now we were able to 3D scan each individual fossil whale, and we have a small 3D print, so we invite you afterwards to come check this out. So here's a small version, you probably can't see it, but we just had this printed out at about 4 feet by 2 feet, and we're looking at printing it out full scale, which is 8 meters, so it'll be about 8 meters long. So that's a great example of us supporting a research project, archiving all this information that is now lost. The site no longer exists. And we have this accurate digital replica. And so again, we're supporting research, and now we're looking at ways to use that data for actual either physical exhibits or online exhibits.
All right.
Okay, that's great. Thanks, guys. And last but not least, Jeff Hosfeld from Whiting Turner.
Thank you very much for having me here. As Jan mentioned, I'm an engineer with the Whiting Turner Contracting Company. I was trained as a mechanical engineer, which is kind of fitting because it sort of links the construction industry with the fabrication of the materials that we use in these buildings. And I know what folks say about contractors behind our backs. We tend to be the butt of many jokes about being over budget and behind schedule on every job, and really it's a result of the industry, the construction industry, being broken. So what I have been doing, along with many others at Whiting Turner, is using technology to help solve some of the issues that cause those budget busts and schedule delays. And we've taken principles from the manufacturing industry, or borrowed them, I guess you could say. One of those we refer to as BIM, or Building Information Modeling. Excuse me. which is building information modeling, which is 3D modeling with a certain amount of intelligence. And by doing this, we can actually do virtual mock-ups in 3D before the building's even built. From there, we can use rapid prototyping with 3D printers to create models and work out construction issues before the shovels even hit the ground. An example here is at Mercy Medical Center, which many of you have probably seen under construction downtown. We took the head wall in each of the patient rooms and we modeled it in so much detail that we could actually have enough accuracy to prefab that entire wall of that room. And there's 190 patient rooms in Mercy Medical Center. So the head wall, as many of you may know, has all kinds of devices, electrical receptacles, medical gas outlets. So there's a lot of piping and conduit in this wall. So by prefabricating this wall, we were actually able to save 3 months in the overall project schedule. As everyone knows, time equals money, so that 3 months equated to about a $4.5 million savings to the overall project and our customer, which they were very happy about. And you can just keep scrolling through the slides here. As you can see, here's portions of that wall that were being prefabricated in an off-site factory, and much of that detail was able to be fed directly into the fabrication machines so that pipe and conduit could be cut exactly to size. So this is a little bit of a bigger scale than the additive manufacturing, but it uses the same principles. In addition, we were able to prefabricate connections to a lot of the mechanical and electrical equipment so that when it comes out to site, it's exactly cut to size and ready to install, saving much time and money. These principles can be applied to even bigger components of buildings. In fact, we see on a lot of our projects opportunities to fabricate bathroom pods, for instance, where the entire bathroom, for instance, in a hotel or a hospital can be prefabricated off-site. Limitations, of course, of size, what you can ship on the flatbed of a truck, but nonetheless, opportunities arise where in areas of repetition, prefabrication can save a significant amount of time and money. In addition, by prefabricating off-site in a controlled environment such as a climate-controlled warehouse, you see a lot of improvements in the quality of work. Take, for instance, an example. I think the last slide in this series here shows a welder that's welding a pipe on site. As everyone knows, construction sites can be very dirty and messy. It's not a very good environment to do high-quality work. A welder, for instance, if they're welding a pipe, will get there in the morning, they're probably grouchy and it's cold outside and it's raining and wet and muddy, and they have to spend an hour or so getting their welding leads out, setting up the pipe, getting ready to weld it. And typically you would see a lower quality product than in a controlled environment, in a warehouse or a shop where everything is set up ahead of time, there's no setup time, and there's no rain, wind, cold, or whatever to deal with. So overall, applying the technology of 3D modeling and rapid prototyping and CNC, we're able to reduce the costs of our projects, improve the overall quality, reduce the schedule, and overall reduce the amount of waste that we see from construction of buildings. Thank you.
Great, thanks. That was great, and I know we would love to hear more from everyone. So this is a Q&A portion of the panel, and so I want to give you time to do that. But one of the questions that came up to me as I was kind of organizing the panel was, I was curious about discipline-specific issues related, discipline-specific issues around rapid technologies. And so if you guys would talk about that, and I was thinking about the Smithsonian, the virtualization of the collection. What is it? We're in a global world. The internet connects us everywhere. How do these technology, what barriers do the technologies present, or what barriers do you encounter? So either issues or barriers to adoption.
So one of the barriers we face, and it's a fairly big one, so we can 3D scan objects and capture the geometry at very high accuracy and resolution. But then when it comes to delivering that content to the world, that's a whole other thing. So we see a lot of developments with 3D viewers that are up and coming, but none of them are quite there yet. But as soon as that nut is cracked, there's going to be a huge demand for more scanning of objects. One of the things we're very excited about on the upside is the democratization of 3D capture tools. So anyone familiar with 123D Catch? So using your camera to take photos of an object to create a 3D model. So anyone you can do it with your iPhone. And we actually use it for some of our work on occasion. So depending on the project deliverable, we might use a $150,000 laser scanner, or we might use our iPhone. So that's the other side. Yes?
Hi, I'm Stacey Wagner. I'm with the National Institute of Standards and Technology. I work in the Manufacturing Extension Partnership. And one of the things, oops, you could probably hear it. So I was curious to know, one of the things that we're working with manufacturers on right now is transitioning them. And I think the recession did a lot of this work for us, but transitioning manufacturers from sort of low-skill, commoditized work into innovation and growth through things like this, commercialization. We help them with workforce skills. And one of the challenges that I'm facing is how we might create enough, as the speaker in the last session said, he can't find enough workers. And I have to say, having been in this for 20 years, this is not different than 20 years ago. Manufacturers have continually looked for skilled workers. So I'm wondering if across all of these sectors that you've talked about, if there's a basic level of education that would allow someone to go through school and then to move into any of the sectors in which you work in this kind of discipline. So rapid prototyping, 3D modeling, all of this, what sort of baseline education would a young person need to get in order to then, so they wouldn't have to make up their mind in grade school that they wanted to go work for the Smithsonian or they wanted to go work for the Defense Department. They could make that choice a little bit later on in life. What do you think they're going to need to know in order to be able to make those choices and then see that through? Because right now what we're seeing is even if kids are making choices, they don't have the educational background to succeed.
I would be happy to address that one. We work very much in teams, and we have so we have different levels of folks with different levels of education that work, and we have over the last 15 or 20 years have grown quite a lot of people. My group's about 130 folks right now. We have probably 20 students that are part of that group, and probably 40 of the people in the group were former students. And we have folks that are in the professional fields that have come up through science and engineering. We also have folks that have come up through technical fields. And education is always good. What we try to tell people is don't learn a specific skill, learn about what it is you're trying to accomplish and ways of doing that, because the skill sets are going to change as the technology changes. But obviously the digital world is becoming a huge skill, and many of us in the older generation are finding that actually the younger generation comes naturally with those skills. But in the technical skills. And, well, one other thing is we've been very good about recognizing the value of diversity in our teams and our workforce. So there's MICA folks here. I have 3 people on my staff that are former MICA students. We have engineering students. We have students from Catonsville's here. We have CCBC, former CCBC students in our group. I think those programs are exceptional in the additive manufacturing world. Those associate programs have been very, very good at preparing our students for. And if they don't come with those skills, we often send them back to get those kinds of education. The engineers and scientists are coming in with a lot of the skills. Part of it they bring with them from birth, I think, and that's this natural. Especially the folks from MICA, it's intimidating to work with them because of the natural talent that they have, and that's something that you can enhance, but you can't put there. But I hope that answered.
It does. I want to just ask.
Could we get to another question? I'm sorry. We only have several minutes left. I'm sorry for doing that.
Hi, my name is Joe Hart. I'm with a local company called Control Cable, formerly with AAI. You had a picture of our Shadow UAV up there, so thanks for the plug. This is a technology question. I guess it's related more to you, Mark, and Dr. Rouse. Metal sintering, the powder process, it's been around for a while. Traditionally, as I recall, you can make a metal part, but it was slow. It was you didn't get the granular structure, you didn't get the tensile strength, and things of that nature. So we heard about advances as far as speed. I just wondering, how it's coming along as giving you a stronger part, and what advances have been made. Thank you.
Dr. Rouse obviously could give a much better answer on the medical part. On the engineering and mechanical aspects, accuracy has gotten very good. In the old days, we used to have to do, when we sintered, it wasn't fully hardened, so you had to go to a secondary process. That added error, and so we couldn't get the accuracy that we needed. With the new, we're currently using an EOS direct metal process, and we're getting the accuracy to melt and again, mixing technologies, we're able to make inserts to go in our injection molds to make high precision plastic parts using direct metal inserts. Yesterday I was watching parts that are going on these little sensors that are going to be dispensed, hit the ground at 40 miles an hour, stand themselves up and talk to satellites, and many of the little metal parts are being built by direct metal sintering.
I think what you'll find now is that whether you're using the SLM, DMLS, EBM, or any of the direct metal processes, you're ending up with a metallurgy that is identical or superior to most of the materials that we've used in the past. Part of the stuff that was presented at the show earlier this week where I was a lot of that information. And if you combine the fact that you've got easily a comparable metallurgy to the product, you have a complexity of your design that's easy to design but unmanufacturable any other way. So you really got the best of both worlds. Sintering, no. Melting, yes.
Questions? Yeah. And raise your hand. We got a microphone over there, and your name and...
Sure. Larry Long with Fast 3D. On these implantable additive manufactured devices, what are the issues with sterility of the process and the parts, and what special procedures, if any, have to be? What kind of, as a manufacturer, or as a producer of these parts, what has to be done that's specific for the medical implantable device market?
Well, for starters, I'd say it's easier for me being a government institution, but for the most part, custom devices that are made for a specific patient by a prescription from a physician don't follow the same category as manufactured parts for sale. That's an entirely different set. But if you look at the fact that whether you're using the EOS or MTT or RCAM equipment, you're not going to get anything that's going to live in a multi-thousand degree furnace in the process of building this part. And when you're through with the part, you put it in a standard sterilizer. So we have had zero problems with being able to achieve a testable sterility of the product. And as long as you're using a tested material, which is what we're doing, we're using a material that's been in use in the human body for a long time. So we're careful on those sequence of events. If you're not in a position where we are, and we will actually do this, having FDA certification of your process and your facility is a very critical thing, even though they can't certify your product.
Thank you. I'm going to ask the last question since I have the microphone, if you don't mind. Yeah, my job for 20 years has been advocating for manufacturing. It's a manufacturing event. We have a professor of art. We have direct dimensions, entrepreneurs. We've got the Army. We've got construction. Art professor, object lab. We have the medical profession. We have museums. So here's my question. Who am I representing these days? Seriously, it's right. The tools of manufacturing are clearly in everybody's, and they're going to be at your home. Talk to Todd Blatt, he's here. So I guess for us, a part of my conversation is, yeah, remember, I'm the guy, gray hair. Hey, I represent manufacturers. So is this the new team? Go for it. Tell me, what do you think? Thoughts, comments? You're getting close to it, because I know Gina wants me to get wet at the construction.
I'd have to say it touches many more facets of our life as technology becomes more ubiquitous. And as a construction professional, we need to understand where the components of our projects, how they're made, and where they're coming from. Because our projects are getting more and more technologically advanced as time goes on. Hospitals and laboratories and all the technology that goes into buildings. So we need to understand and work with the manufacturing industry to help improve those processes to work with our industry better. And I think that would go for all the industries that are being represented here today.
It's going to be fun figuring that out, too. And I love the slides. I love the world of work that you guys are doing, and girls. So, yes, Mark.
If I can give a little, I'm obviously with the Army, a federal lab here, and we do rapid, we do self-sustaining, high performance, and it almost sounds like an oxymoron, doesn't it? But how could we do that if we didn't apply this kind of technology? It's the enabling thing that allows us to do those things.
And I think that's one of the things. There's a new kind of glue out there that's going to connect all of us. Let's give this group an applause here, folks. Thank you so much.